Welcome to the workshop. So the workshop, we broke it up into two parts, mainly just because there's a couple of different topics that could be covered in this. I've taught this EMF workshop a couple of times. So I'll just give like a brief introduction of like who I am and whatnot, just because it's all being recorded. But the focus of this workshop is learning about what electromagnetic frequencies are, how we can detect them, what they sound like, and all the fun stuff involved in that. So those of you will already know a lot of this, but I'll just say anyways, for those who don't, you can even read my notes that I'm gonna read as well, because I'm just projecting it. But I've basically been doing hardware electronics projects for about the past 15 years or so of different flavors. Started out with circuit bending, then it went on to synthesizers. Now it's kind of like moved on to like exploratory sensing through e-textiles, through different like interactive technologies. Now I've moved on to EMF as like the next hyper-focused, fascinating thing that I've been focusing on. And I've also been working with like sensors for environmental purposes and whatnot. But for this past year, I have basically been doing a deep dive into electromagnetic frequencies, just because I think they're so cool. Everything that I learn about it, there's just like a new layer of the rabbit hole that you can like learn about it. And so I just thoroughly enjoy it. Yeah, I used to run the one of the maker labs at PCC. You can ask Michael about it if you're curious about it, about that for future conversations. And like Nandini said, I've also taught workshops here and at Make Think Code previously. And other than that, I teach a lot of workshops at hacker spaces, different universities, and I go to a lot of hacker camping events. And that's primarily what I made this board for. And so the EMF Explorer badge, I made it to be something that you don't need to have a lot of technical background in order to understand how to use it. It's made really just as an exploratory device to kind of get people to become more curious about their surroundings. And I originally designed it to be used at a hacker camp. There's a couple of them. There's one called Tour Camp that happens every other year. That's the American Hacker Camp. It's just a bunch of nerds in tents in the woods hanging out with fast Wi-Fi. So it's a really good time. So the scenery for the board, it has like a little camping scene on the bottom of it. So it's like, it's all about that. But I made it to be portable because people will wear different badges around on lanyards at those events. And so I use it for that, and I also use it so that way it acts like a spotlight because nobody brings a light with them at night. It originally kind of came about, I'll just show some of the previous work. This was a previous badge that I did. This one has batteries. This was a previous one that I did that I took around to hacker camps all over the place. And this one is set up so that way it glows through the front just like this one does. But this one has like color changing LEDs. This was one of my first bigger deep dives into PCB design and understanding how to turn PCBs into works of art, essentially. So that's a whole topic that we can totally get into if people are interested in it. But so this is kind of where it started, and then this is like the next iteration that I wanted to add some functionality to it so people can go exploring with it, other than just having a cool nightlight at night. And so, and also as a part of this whole thing, a part of this whole venture, I wrote an article about it that has come out in Make magazine. It just hit the shelves. So a part of this is kind of like a little bit of promotion for the article. And the article in the magazine, it's in here somewhere. I should have put. This is the August one. They said that it hit the shelves like August 15th or something like that. And so the article that is in here, it's all about this badge, but it teaches you how to make it on a breadboard, so that way, or on a piece of proto board, so that way you can assemble your own. So that's essentially kind of what we are doing here in the workshop, except since we're working one-on-one in this capacity, then we can talk about whatever we want, and that's really exciting. And so that's something that I kind of wanted to check in with everybody and see, because like I can get up here and just talk about this forever, but I'm really curious to know what it is that y'all are interested in with this, because I went ahead and listed out some of the topics of the things that we could talk about, but I'm just kind of curious like about what your background is, what your interest is, and what you're hoping to get out of this workshop. So I guess, like I mentioned, we could talk about the circuit design. We can build the circuit on a breadboard and learn how to read the schematic for it. But we can also get deeper into the design side of it, how to make your own PCBs, how to make custom pieces of art with circuit boards. We can even go as deep as talking about how to then manufacture that, how to order the components, how to get a factory to make it for you. It goes deep. So I would love to take a moment to go around and check with everybody, hear what you're interested in, and hear what you're most excited about. So I guess I wanted to talk about what EMF is a little bit. So there's a whole, in terms of electromagnetic frequencies, there is a huge spectrum, like Wi-Fi, Bluetooth, X-rays, all visible light, just everything is emitting EMF. Our bodies do. Every time your heart beats, there is essentially EMF that is coming off of all of that, of different degrees and frequencies and intensities and whatnot. And so the circuit that I have built, it's a pretty basic circuit. It's all analog. And so this just has an amplifier chip on there that is amplifying whatever these are picking up. It amplifies it up enough that way it can drive a pair of headphone speakers, so that way you can listen to it. So it's picking up a larger frequency range than what we can perceive. And so the sounds that we're actually going to be listening to is going to be in the extremely low frequency range. Humans can hear up to about 20 kilohertz. I tested myself, I was like around 13 or 14 because I've listened to much loud music in my life. So it's quite low. Luckily for us, pretty much most of the electronics that are all man-made, all electronics are man-made. It all falls within the human range of hearing of the frequencies that come off of it. So we won't, but I mean, once it gets up higher in terms of like Wi-Fi and Bluetooth and things like that, those are oscillating at such a fast frequency that our ears can't perceive it because it's such a high pitch. It's not in a format that we can hear. It's not sound waves, but when you convert it to sound waves, we can't perceive it because it's just so high pitched. It'll pick up any electronics that we can find in the room. I think that if this was pitched up so that we could perceive the higher frequencies, it would be going off all the time. We're surrounded by Bluetooth and Wi-Fi and all of that. So in a way, it's like a little bit more beneficial because then we can hone in on the objects and like hear what each object sounds like. Let's see. And so I have an illustration that kind of shows like somebody like emulated what the EMF looks like. And so like for your cell phone, if you listen to it, there's going to be like probably like 10 different sounds just on this alone from the different parts on the board that are doing different functions. Same thing with your laptop. It's just so much. We have somebody joining. And so, yeah, and so this is also like an important consideration when people are doing circuit design. You have to watch out, especially for this other one that's a real simulation from Altium, I think, is the PCB design software. And so you do have to consider that for components that are too close to each other, like capacitors tend to be really resonant. And so there will be like cross-contamination in terms of sounds and things. Yeah, so I think that this is a cool visual because it visualizes the EMF that you would otherwise be hearing. So it's just kind of helpful to kind of put the context to it. And so for the circuit, this is like the most that I could break it down for what's going on. But these inductors are the things that actually pick up the sound. And the inductor is just a tightly wound coil of wire. And so that tightly wound coil of wire, whenever EMF hits it, it reacts to it in a way that it then picks up those vibrations and converts it into a voltage that is on the board. And so that current, essentially, then that it is picking up, then it goes up to the op amp that I have on here that is then amplifying that sound. And then that amplified sound is then enough to drive a pair of headphones or a speaker, whatever you plug into it. But the thing that I think is really fascinating about it is that you're going from a coil of wire, amplifying it, and then using another coil of wire to listen to it. So like that same super basic concept of having like a wire coil and then a magnet in the middle of it, it crosses so many different spectrums in terms of how you can use it, which I just think it's really, really neat. And so then once this slide just kind of goes into it a little bit more about just like that, the waveforms that it's picking up, that is what's driving the speaker coil back and forth because it has a magnet in there. So as the signal that comes in, which is an AC signal, it's crossing above and below the middle point on there, it's driving the speaker coil back and forth and back and forth. And it's doing it so fast that you can't quite perceive it, but that produces like the sound that you're hearing. And then it converts into sound waves that we can hear. And so with that being said, I think we should build a circuit because I think that'd be fun. Let's see, so I will grab the components for everybody. We have breadboards for everyone. Yeah, I just went ahead, I just threw these up here. I just found them on the internet or whatever. These are just like different symbol representations for the different components. I outlined in red the ones that we're going to be using, but this just kind of shows like the representation of like what the symbol looks like for the different components, just to kind of familiarize with that for if folks aren't familiar with this. But I have the whole schematic drawn here. This is the entire schematic for this board. And so this is a schematic that we're going to be building. And I'm happy to walk through the whole process for that and help out with it, because there are a couple of little gotchas for it that I'll show. I have the actual chip itself on here so that way you can know what the pinouts are. The op amp, it's a dual op amp, so there's two amplifiers inside of it, and so that is represented by then pin 1, 2, and 3. That's the first one, and then 5, 6, and 7 is for the second one there. So I just have that up there to make it easy. We can geek out about the actual gain formula that created the gain for it. The gain of it that amplifies it up, it's determined by the RF and the RN. It's the feedback resistor and then the input resistor. And it's essentially the RF divided by RN equals the gain. I'm just amplifying the shit out of it, like as much as this chip, I'm just throwing it all at the chip, as much as it can handle, so. And so also for this, y'all might need this if this image changes. I have this same schematic on my GitHub. And so for there, it has in the code under the KiCad files, there is a link for the PDF there. And then this is that same schematic. Let's see. But you might want to grab a picture of this or look up the pinout for it. Let's see, a TL072 pinout. This is actually a good one, yeah. So just Google for TL072 pinout. And that is just another op amp that has the same pin configuration. And then you'll have that in the background. And even that one, it is drawn slightly different, but it's the same connection. It's just the image for it is rotated. Okay, so let's see, make sure that we can see all of this. The main thing, probably what I would recommend to start with is get your power all set up for this. I don't know how well, I want to make sure that, I don't know how well you can see it, but if you look at your schematic and it has the power connections on there, it's the stuff on the right. Does everybody have it pulled up? Okay, so whenever you look at it, one of the things that makes this circuit work is that we have, like if you're reading the power strips on here or whatever for the circuit, there is a positive 1.5 volts, which is down here, and then negative 1.5 volts, and then ground. So there's actually 3 different power connections. And that's going to be important for this circuit because we need to give the amplifier AC power so that way it can amplify it within that power range that we've given it. And so the way that you do that, you see the AAA battery right there, that represents the 2 cells. And so if you look at your battery compartment, it has a plus and minus in there for the positive and negative. So I just went ahead and stuck the positive of one side of the AAA battery into the breadboard, into this bottom positive power rail here. And then for the other side, for the negative 1.5 volts, I'm sticking it into the negative side of the top here. And so now this will match it so that now the top negative rail is this top one, which is going to be negative 1.5 volts. And then the bottom plus rail is going to be the positive 1.5 volts. And then to get that ground, it's a little hard to see. You'll probably have to bend your stuff out of the way. Then this is, you're going to take another pin connection and you're going to bridge the plus and minus right there at the bottom. So it's like as if you're wiring it up in series, but you're going to tap into that, and then that will be your, like, essentially it's like a virtual ground. And for that, I'm just going to run that down to the bottom. There we go. So there. So now it's set up so that I've got negative 1.5 on the top. The virtual ground here, we're just going to ignore this switch. We don't need that switch. So that's going to go to the bottom. And so that is, this one, it looks funny because it's flipped over right now. Usually that would be flipped down, but it indicates the same. So that will be for anywhere that it says ground on the schematic. It says it in multiple places. That's all going to connect to that same ground. The only thing that is going to connect, the only place that the positive 1.5 volts and negative 1.5 volts are going to connect to is the actual chip itself. And so you can see on there that's indicated by pin 8 and pin 4. It's listed on the schematic. And so if you look on your schematic where it showed the positive and minus, that shows it has the pin numbers there of pin 8 and pin 4, and that's the power for the op amp, which is, our op amp is this NJM2115D. That's what that part is. So then we know that pin 8 is going to go to positive, which is the last leg there. So that's going to go down to that. And then the negative is pin 4. I mentioned. So then pin 4 off of the chip is going to go to that negative rail. So that is the negative 1.5. And so then and I want to make sure everybody gets to this point also. And so from there, I'm going to go ahead and connect the ground that's coming off of the chip also, which you can see on the schematic. It shows pin 3 goes to ground and pin 5 goes to ground. Also wait for us to catch up to that. But that is essentially your chip needs to have 4 different power connections going to it. Okay, and so once that is all wired up, then you can go ahead and start with the rest of the circuit. And so let's flip it like that. Of course, reference the schematic that is on your computer so that way you'll get a better image. But for the inductors, it's represented by these 2 components right here, these 100 megahertz. And so these, they can go in either way. I like to just kind of have them hanging off the edge of the board. And because it's going to be connected to ground on that common middle point, I like to leave a little spot there in the middle for that to happen. Oops. And so to make that connection, I'm just going to bridge those 2 middle points together. You know what, I'm going to change my mind. I'm going to pull it out. I'm just going to bridge it like this, so that way they're both on the same rail. And then because it has what I'm looking at, because they're tied to ground there, since those are both on the same rail, I'm just going to pull that down to ground, and that'll be that ground connection. And the 2 components that I haven't put on there yet are these 10 microfarads that are being pulled to ground. That's a low-pass filter, technically, is what that's doing. So I find that it makes it sound a lot better. Personally, I like it. And let me think about the best way. This side, there's enough that I can bridge that to right there. So let's see. Yeah, these LEDs, they all seem to kind of make the same sound for it. And then even this is putting out Wi-Fi. Nice.
Feedback.
It sounds kind of... So previously we were just looking at a PDF of the schematic, but that was just a screenshot of the KiCad, you could say it either way, of the KiCad schematic. And so KiCad is a free and open source PCB design tool that I use for everything. I really like it. There is a bit of a learning curve, but once you know like the basic intro steps, it's not too bad. Adafruit has some good tutorials for it. I love Adafruit tutorials, so without boring you with all the minor details, I'll just give the overview for it, just so you kind of know what you might be getting into. So I drew everything up in here. Every component you could ever imagine is basically already in KiCad. You can make new components if you need to, but it just has a huge library of like everything you could ever possibly want, which is great. And a lot of times it'll give you a view of the footprint of what that is going to look like also, so which is really handy. But essentially what I did is I went through and picked out all the parts that I wanted, and slowly built it up on here. You can use the wire trace tool and you can make different connections and bridge things together. But I was able to draw everything out. And I built it on a breadboard first before I got to this stage and got it how I wanted, and then went back and retraced my steps and built it as a schematic. And then so in the schematic, like this represents what is happening, where all the connections need to be for it. Because then whenever you pull it into your PCB, this is the completed view for it. But just as an example, it'll have these traces here. We call these rat's nest lines because it literally looks like a rat's nest when you pull it all in at first. But so it knows that because it's connected, this battery cell is connected in the schematic, it knows that that connection needs to be made. So even though it's broken right now, it's going to hold on to that memory of it so that way you'll know where the connections need to be whenever you're wiring it together. And so, for example, it knows that this battery cell connects to the other battery cell, this with that common ground that we saw, and that it then goes up to the switch that we didn't use. And so it won't let me make any other connections except for that one that it thinks that it should make. So that's really helpful, so that way it'll make sure that you're not gonna mess up any of the connections later on. So it has that memory is really helpful. And so whenever I did this, first I built all of this out. Like usually what I'll try to do, tools, assign footprints. I would go through and I would assign the footprints that I wanted first with this footprint assignment tool. And so it knows that, those are filters, open up the footprint viewer. So it knows each component, what the footprint is going to look like. And so I did this first, just kind of knowing what parts I wanted to use. And so then whenever I brought it into the PCB, it drops all of the parts onto the board with that footprint already assigned, with all the connections made. And if there wasn't a footprint assigned to it, whenever I would first open this up, it would throw an error saying, we don't know what this part is supposed to be. So you usually want to assign all of the footprints on this side first before you go over to the PCB side. And you can make changes over here. Like say I changed my mind and I wanted to use like a different holder for the battery or something like that. I could change the footprint, say I'll just change the selected footprint, and then I can go through and pick out which one I wanted it to be. And it has images for everything. And so you can reassign stuff that way. But if I did that, if I changed the footprint on this side, now it's separate, it's like broken from what the schematic was. So that if I did update PCB from schematic, it would then try to pull in that original footprint that the schematic had assigned to it on that side. So it's helpful in the beginning to get you started, but after a while, I tend to kind of deviate away from what the schematic originally said. That's not the best PCB design hygiene process, is what I call it, but that is just something to keep in mind, that unless you're doing major changes, I will turn away from it. And so then I eventually pulled all of the components in. There's different layers to the board. That's all separated over here. This is the front copper layer. This is the back copper layer. There's the adhesive layers that I'm not using. That's if you're doing surface mount stuff. Same thing for the paste. That would be for the solder paste where it would be applied, but this is all through hole. Then there's the back silk screen, front mask and back mask, which is for that centerpiece there. And then a bunch of other layers that we're not using. You can preview what your board is going to look like at any point by going up to the 3D viewer. And this gives you a 3D view of what your model is going to look like. And so I find this really helpful. For the inductors, I just took an LED footprint and then modified it. So it still has the memory of the 3D model of the LED, but I'm not using it, so whatever. But I modified the footprint to space it out and give it these extra traces that you can anchor the inductor down onto. So for this one, I just am playing with the solder mask layer and then the silk screen layer, which is on the top. And the silk screen is typically used just as to indicate the different part numbers and stuff on the back. That's what its function is, and for any labels that you want, but I just went nuts with it and just used it all as art. Because I think it's fun. And I really like doing circuit board art just because, one, why not, but also I got into it because this was cheaper than designing enamel pins. And so like this is a PCB, this is a PCB, and this is a PCB also. And I have a bunch of examples of different art boards in my box. But this cost about 10 cents to make versus if it was an enamel pin, it would be several dollars just for one of them. Like this, I think I bought it for like 10 bucks or something. So from a cost scale, I think that it's really fun because you could just kind of crank out these custom pieces of art that you would wear as pins that would otherwise be a lot more expensive to manufacture. And you have to make them in bulk and then you'd be stuck with a bunch of them, It's a logistical thing. So so this is how the board is designed. And of course, there's a ton of other stuff that I'm not mentioning with this. This is handy because then you can like hide different layers and focus on the ones that you want. If you're drawing traces, you can do it just from the backside. And like I mentioned, it always has that memory of where it's supposed to be connected in the schematic. So it'll only let you make those connections on the board. And for the art for it, I used Affinity Designer to make everything. You can use Adobe Illustrator, you can use free tools. I like Affinity. It's a one-time payment model for their design software. So it's basically the replacement for Photoshop and Illustrator. And it's way cheaper, and I like it so much more. So I was able to do everything on here. Drew everything. I think I drew it all on like an iPad first, and then I used Inkscape to auto trace it and turn it into a vector outline, which is another free vector tool, and then pulled it into Affinity Designer where I then went and modified everything. And so this is just one giant vector that you can go in and modify it. And so a helpful tool for all of this that I have found to be a game changer is this project called Gingerbread. It's this artist, she runs a company called Winter Bloom. She makes Eurorack synthesizers. And this is a tool that allows you to pull your Affinity files in and get a preview of what it looks like. It's really accessible. She has a one-page guide for the docs about how to set it up. So you need to set up the DPI for your Affinity settings, and then it tells you how you should label the different layers. So there's a front silks, back silks, front mask, front copper, back copper, and edge cuts. Those are the main ones. So for over here, I've labeled that as the front mask and the back mask, and then the front silks and the edge cuts. I don't have the back silks on this one, just because I don't. But so then, once I have that exported as an SVG, I can just drag and drop it into here, and it gives me a preview of what it's going to look like. And it's just so handy. You can change the mask color, because you can get PCBs in all sorts of different colors. You can change the silk screen color. Some fab houses will change it. Most of the time you want to leave that as white. And then the mask opacity too. That's another feature. You can change which ones you're looking at and stuff. So I just find this to be a really helpful tool. And then if you like it, you can download it, and then this will download it in a format that works for KiCad, or you can just copy this and then go into KiCad and paste it. And this one pasted all weird because the file's not optimized correctly, but it will bring in the file with all of the layers already put together. That one didn't, because it's not made to be perfect yet. And I find that to be so much easier. Previously, to get these art layers in here, I had to do import graphics and then find the layer for it. I don't know if I'm not gonna try to pull it in, but typically you would pull something into here, and then you can assign what layer you want for it to be applied to. And this works. You can do it this way. This is how I used to do it, but then it's like you have to then go in and perfectly line the two layers up. It's all separated, and it's just a lot harder to work with. So I find using the gingerbread tool as like the middle ground for it is a lot easier, because it'll stitch all those layers together and have them assigned to the correct layers, whether it's a front mask, front silk screen, or whatever. And I just find that really helpful. Whenever it is done, whenever you have a board that you want to order, I always recommend people use Oshpark for their first PCB runs. They are local. They're in Lake Oswego. Very cool people, very supportive. So I always like to recommend them, but it's more expensive. And so for a prototype run of like 3 of these, it has free shipping. It would be about $50 for 3 of those boards. But it's fast, it's easy, you don't really have to think about it, and I just find it really helpful. And I like it because whenever you are going through to order your board, it shows you what it's going to look like, and it shows you what the individual files look like and everything. So this is a really good sanity check, just to make sure that it looks the way that you want it to. And I guess one thing I didn't say, to get this file, you would go to, like when you're ready to export everything, you would go to fabrication outputs, and you would go to the Gerbers for the fabrication output. For whatever reason, they're called Gerbers, and that is all of the files that the PCB fab house needs in order to know what you want to make. And so it breaks down into like the drill file, the front silks, back silks, board outline, all of that. And so you would just export all of that and then import it, and then it gives you the preview of what that's going to look like. But yeah, I will be teaching another workshop specifically about KiCad where we walk through the process of designing and ordering our first PCB. So that'll be really fun. So it'll kind of help to like demystify all the steps in between that I haven't mentioned about this. But yeah, that is the majority of everything. There's all sorts of other details we can get into, but based off of the time, I think that's it.